Hey there, let's solve this LeetCode problem. You're given an array of positive integer. You're also given the queries array. We have to find for each query the XOR of elements from left to right. Now we can see an example. We have 1, 3, 4, and 8. Our array is 1, 3, 4, and 8. And we're given the query from 0 to 1. This just means that take the XOR of elements from the index 0 to index 1. So this will be 1 and 3. Just to remind you what is XOR, it's a bitwise operation. You can think of it as a function. It takes 2 bits. When the bits are, let's say the bit 1, let's just call it bit 1 and the bit 2. And when the bits are different, it outputs 1. And when the bits are same, it outputs 0. So for 1, this is the binary representation of 1, 0, 0, 0, 1. And the binary representation of 3 is 0, 0, 1, and 1. We take 1 and 1, this is the same. We'll have 0, 1 and 0, we'll have 1, 0 and 0, we'll have 0, 0 and 0, we'll have 0. So this is 2. For the first query, the answer is 2. For the second query, we have 1 and 2 from 1 to 2, from 1 to 3. So here we have 3. Let me actually try it again. I shouldn't have deleted. Now from 1, the index 1 to 3. So we have 3 XOR 4. We have 3 as 0, 0, 1, and 1, and 4, 0, 1, 0, and 0. 1 and 0 is 1, 1 and 0 is 1, 1 and 0 is 1, and 0 and 0 is 0. This is 7. We have here 7. This problem looks like the prefix sum, right? You're given usually an array of integers. Let's say you have 1, 2, 3, 4, and 5. And you might given queries. Let's actually put the indices 3 and 4. And you ask the query, let's say, find the sum from index 1 to 3. The easiest things you do, if there's only just one query you can do, you can just go from index 1 to 3, adding all the elements. For this problem, we can also do that. That is a brute force approach. But this would give us a O(n) algorithm. So this would be quite slow. In fact, if we have n queries, and for each query you might do, if we have m queries, and we'll have to traverse the array n times. So O of m, now let's just suppose that it's O of n squared. This would be quite slow. So we wouldn't do that. We have 1 and 3. How do we do that? 2, 3, 4. We know the prefix sums. You probably solve a few problems with prefix sums. Let's allocate, actually, we usually allocate one more. Here we put the 0. I'll talk about the 0 later. And then we have the next of the elements. 0 plus 1 is 1. And 1 plus 2 is 3. 3 plus 3 is 6. 6 plus 4 is 10. And 10 plus 5 is 15. So we have 0, 1, 2, 3, 4, and 5. So for example, if we're asked to find the sum from 0 to 4, the index 0 to 4, this, since we use one base index here, actually the first element is 0, so this would correspond to 1 to 5 in our prefix array. So 1 to 5, so from index 1 to 5, the 0 to 4 is in our array is the sum of all the integers, and we have 1, 2, 3, 4, 5 in the prefix sum as indices from 1 to 5. So we can look at this spot here at index 5. We have 15. Now what if we asked from 1 to 3? This corresponds to 2 to 4 in our prefix array. So this part here, let me change the color. From 2 to 4, this element, including this element, and this element. This is 2, 3, 4 in our original array. Now, how do we find this? The one thing that we know is the sum from the index 0 to index 3. So this corresponds to the sum from index 1 to index 4. We know this sum. In fact, it corresponds to this sum here. And you can notice one thing. If we can undo this process, if we can undo the addition of elements, which is undoing the addition, basically this is the inverse operation of addition. It's subtraction. So we can subtract this part, this overlapping part, from 0 to 1, not 3. 3 is included in our query. So 0 to 1, then this will give us the answer for the range from 1 to 3. So we have 3, 6, 10 in this range. We have 2, 3, 4 in this range. So the sum from 0 to 6, 0 to 10 is 10. We subtract this overlapping part here, which is sum from 0 to 1, which is 1. This is going to be 9. So the answer for the query 1, 3 is 9. It's 2 plus 3 plus 4, which is 9. Let me actually remind you of what we did with the prefix sum. Let's say we have an array 0, 1, 2, 3, 4, and 5. And the values are not important. What we do with the prefix sum, we calculate the sums up to some prefix. We know the sum up to this prefix and this prefix of this prefix from the first element to this index, from the first index to this index, and from the first index to this index here. We know all this. We know all this prefixes. Now, when we ask a query like L to R, now what do? Let's suppose that L to R is this part. I mean, this 3 elements, 2, 3, 4. Now, then the sum, we have one part here, which is the whole prefix from 0 to R, and there's an overlapping part. If we subtract from this prefix sum from 0 to R, this part, then this would leave us the desired range, all L to R. So we have sum of L, R. So this would be sum from 0 to R minus sum from 0 to L minus 1. We don't say L because L is already included in this range, this 3 elements here. Now this gives us a nice way to solve the queries with addition. So why this works? Why here this works? Now let me explain it with another example. Now let's say we have 4 elements. Now if we want to find the sum from this index 1, from index 1 to index 3, with our according to our formula, it will be from index 1 to 3, it will be sum of 0 to 3 minus 0 to 0, which is just a single element here. So we subtract this from this to get the answer for the range 1, 3. And why this works? The reason it works because the subtraction is the inverse operation for addition. So you might wonder if there's an inverse operation for XOR. I mean, we could take the XOR of every prefix, and when we're asked when we're asked to find the element, the XOR of elements from left to right, just like this one here, for example, from 1 to 3, we could just use this formula again, but without this negative. So the subtraction is for the addition. It is the inverse operation of addition. So the question is XOR is inversible? Is it inversible? I mean, if we have the XOR of this part, the whole part here, can we do something about this part? And we could do something with this part and this whole part, which will give us the answer for this range here. In fact, we can. This is the fundamental property of XOR. Let's say we have two values, two binary values. We have 1, 1, 0, and 1. If we take XOR, let's call the first one A and the second one B. And if we take XOR, 0 and 1 will give us 1, 1 and 0 will give 1, this will give 1. The same bits, this will give 0. Now let's call it C. Now if you take B, one of the operands, and the result C, and if you take the XOR of this two, this will give you A. And if you do the same with A XOR C, this will give you B. So this reverses it, just like the addition. If you have 2 plus 3, which is, again, I'm running low. Every time I'm running low when I'm recording a video. 2 plus 3, which is 5. Now if you take 5 minus 2, this gives you 3. 5 minus 3, this gives you 2. Now you said we take the minus. So you see, in order to reverse the addition, we use the minus, the subtraction. But in order to reverse the XOR, we just use XOR itself. So XOR itself is the inverse operation of XOR. So we can just use the XOR just like we used addition. We can use this formula. We can calculate for every prefix the XOR of element from the first index to add all of the other indices. And then when we ask the query from left to right, just like this one here, we can use this formula. And you see the property of XOR, the inversible property of XOR, lets us do this, just like we do with the addition. And this is the code. Here I allocated the space for the prefix array. So actually it's not prefix sum, it's XOR. The operation is not addition. We're not summing, but we're taking XOR. But let's just refer to it prefix sum. Now this is the usual setup for prefix sum. We allocated one more space for the prefix for our formula to work when we're asked from 0 to something. If we need to find from 0 to 5, so our formula would be 0 to 5 sum of 0 to 5 minus sum of 0 to -1. So for this -1 to work, we just allocated one more space, and actually our prefix sum starts at 1. At what resides in this 0, this index 0? If our original array is of length 4, we allocate length 5, and at index 0 is the identity element of the operation you're taking. For XOR, the identity element is 0. Basically, what is an identity element? For example, 0 is also an identity element for addition. So basically, an identity element is an element that does not change the value when you apply the operation. Let's say you add 0 to 5. This does not change 5. It just gives you 5. For example, for multiplication, the identity element is 1. You multiply any value by 1, you will get the same value. For XOR, this is this is the same if you take, for example, this binary value 1 1 and XOR it with 0. Let's say the 0 has all the zeros. You will get, for 1 0 you will get 1, you will get 1, for 0 0 you will get 0, and for 1 and 0 you will get 1. So you see 1 0 1 1 is the same as this one here. So for XOR, the identity element is 0. So what resides in that spot, the first value, is 0 for basically the identity element. And then our actual summing, actually not summing, XOR, taking XOR starts at index 1. And then we answer the queries in O1 with our formula. This is an O of n, so a linear time algorithm. For what we do here, we have the p sum, the query, we just add 1 to the index of the right boundary. We have L and R. This is because we have we allocated one more space, and it just happens that we does not subtract anything from the left boundary because we already allocated one space for that. So basically this is the code, and I've actually run this code before, but let me just run it again. So yeah, this is the code. So yes, this is the code. You can run it and it will work. And I will let it run this one, and I will let it run this one. You can run it, it will work. So I hope you learn what are prefix sums. So yeah, this is the code. You can run it, it will work. So I hope you learn what are prefix sum, or at least you're reminded of them, and how you can use them in different situations. Although we don't have summing here, if we don't have addition here, we have XOR, but XOR is inversible, just like the addition. So we inverse the addition with the subtraction, and we can inverse the XOR with itself. That's a property of XOR, and I want you to remember that, and it will be helpful with other bit operation problems. This is if you knew. So the next time when you have something with XOR, or maybe querying or some other property, you can remember this. You can remember that the XOR inverses itself, and this might help you. And you can actually might want to remember the identity element that we put at the first index at index 0. This might seem like inappropriate at this moment, but at other moments they might be helpful. So I hope this was helpful, and see you in the next videos.